Welcome back to the computer graphics course. In this video we start discussing geometries. In computer graphics we have a virtual world containing objects. The virtual world is a space and objects are shapes. Both the space and the shapes are examined by geometries. On the other hand, instead of proving theorems, we want the computer to work with geometric objects, and the computer is able to do calculations on numbers. So all geometric concepts must be translated to concepts that can be described by numbers. So we need an appropriate algebra expressing geometric relationships. So in order to start studying computer graphics, we need some knowledge of relevant geometries and algebras. Let us start with the most fundamental and the most well-known geometry, the Euclidean geometry of the two-dimensional plane. This Euclidean geometry had an enormous impact on science and defined the procedure of modern science. Namely, we build upon a small collection of postulates or axioms that reflect our everyday experience, but after accepting them, we do not doubt them, and all other theorems of these scientific fields can be proven by logic inference based on the postulates. Let us see some of the axioms of Euclidean geometry presented not in the form as suggested by Euclid, but I use a more modern formulation of Hilbert. So the first postulate is that 2 points define a line, and the second is a line has at least 2 points. The third is the most interesting. If we have a line and a point outside of this line, then there is exactly one line that goes through the given point but doesn't intersect our original line. In this case, we call this line parallel line. In order to allow measurements in space, we have additional axioms, like for example, when we move something in space, nothing changes. And when an object is cut into smaller pieces, the sum of the pieces is equal to the original object. These axioms are based on experience, but as we cannot experience everything, they also contain a huge amount of religious belief. In addition to defining these basic truths, axioms have a second important role. Namely, they define the basic concepts. For example, how we should interpret the concept of point or line. These are not defined in a geometry, but axioms talk about the properties of points and lines. So when it comes to the interpretation of the line, we have to think of an object which has properties formulated by the axioms. Having established the axioms, we are ready to prove theorems. For example, our first theorem is the following. Two different lines can intersect each other at most 1 point. So it is not possible that we have two lines that intersect each other at least 2 points. The proof means that we have to trace back this statement to the axioms. The logic of the proof is the logic of the indirect reasoning. So let us assume that we have two lines that intersect each other at least 2 points. However, according to the first axiom, 2 points define a line unambiguously. So these two original lines cannot be different, which is just a contradiction concerning our indirect assumption. So the original formulation of the theorem is valid. Our second theorem is the following. If we have two lines drawn in red color in this image and a third line that intersects both lines, then these two original lines are parallel, which means non-intersecting if and only if these two green angles are equal. The proof is the following. Let us examine whether we can have an intersection of these two lines in this direction. If there is an intersection here, there must be an intersection in the other direction as well, because the situation is exactly the same from the two directions. However, according to Theorem 1, it is not possible that two lines intersect each other at 2 points. So the only scenario is that there is no intersection in this direction nor in the opposite direction. Our third theorem is a very famous one. It states that the sum of the angles of a triangle is the half of the total angle, which means it is 180 degrees. So let us prove this. Let us draw the lines defined by the pairs of the 3 points, and let us select one line and draw another line that crosses the third point. According to the third axiom, there is exactly one such line. Using the second theorem, as these two lines are parallel with each other, these two angles must be equal, and similarly, these two angles must also be equal. So we can see the 3 angles of the triangle together here, forming a half angle. As the total angle is 360 degrees, the half angle is 180 degrees. Well, we can continue proving theorems, but we are not going to do that, because that's the path of a mathematician. Instead of proving theorems, let us ask a practical question. Geometry in Greek means the measurement of the earth. So is Euclidean geometry appropriate for measuring the earth? Surprisingly, the answer is no. The Euclidean geometry is not a valid model of the geometric concepts on the earth. For example, let us examine the parallel axiom. If two people stand on the equator and start moving into the direction of the North Pole simultaneously, then they walk parallelly in the same direction. However, after walking 10,000 kilometers, they will collide. So on the Earth, there are no parallel lines, and all lines intersect. Of course, we know what the problem is. Euclidean geometry describes flat surfaces. And the Earth is not flat, it's spherical. So to have a valid geometry for that surfaces, we have to consider other sets of axioms as well. But before doing that, we have to get acquainted with the concept of curvature. Let us consider first the curvature of planar curves. I give you 2 different definitions, and we will see that the 2 definitions are equivalent. The first definition is based on physics. Suppose that we travel along this red path. The curvature at a particular point is the centripetal acceleration needed to keep us on this path. The second definition of the curvature is the reciprocal of the touching or so-called osculating circle. We can see that the 2 definitions are equivalent by considering the centripetal acceleration of a unit speed motion. According to the formulae of circular motion, the centripetal acceleration is the velocity square divided by the radius. If the velocity is 1, then the acceleration itself is just the reciprocal of the radius. When we are traveling along a path, it's different to turn left or to turn right. We can express this information by assigning a sign to the curvature, and we can say, for example, that if we turn left, then the curvature is positive, and if we turn right, the curvature is negative. Based on the knowledge of the curvature of curves, we can define the curvature of 3D surfaces. Suppose we stand on the surface orthogonally to it and select a given direction in the tangent plane of the surface. Considering the curve that leaves this point in the given direction, we can use the definition of the curvature invented for curves. So for this curve on the surface, we can determine the osculating circle and computing the reciprocal of the radius, and we can obtain a curvature for this particular curve. This curvature depends on the selected direction. That's why it is also called directional curvature. If we go through all possible directions, we will realize that the curvature has a maximum and a minimum in two orthogonal directions. These two orthogonal directions with minimum and maximum curvatures are called principal curvature directions, and the corresponding curvatures are principal curvatures. Having these principal curvature values, we can define the Gaussian curvature of the surface as the product of the two curvatures. Let us take a few examples. So what is the curvature of a plane? If we are standing on a plane, no matter which direction is selected, the direction defines a line on the plane with curvature 0. So selecting two orthogonal directions, in both directions the curvature is 0, so the product is also 0. So Gaussian curvature of the plane is 0. Interestingly, the Gaussian curvature of a cylinder is also 0, because here the principal curvature directions are this direction and this direction. In the second direction, the curvature is just the reciprocal of the radius of the cylinder. But in the other direction, we see a line with curvature 0. If we have a product and one of the factors is 0, no matter what the other factor is, the result must be 0. So these two surfaces are similar with respect to curvature. As a result, we can unfold a cylinder without a distortion. It is not possible with a sphere, because a sphere has a positive curvature. If we stand orthogonally on the surface of a sphere and we select directions, in an arbitrary direction we can see the so-called main circle of the sphere, which has the radius that is equal to the radius of the sphere. So selecting two orthogonal directions from these arbitrary directions, the principal curvatures will be the reciprocals of the radius of the sphere. Therefore, the Gaussian curvature of a sphere will be the reciprocal of the square of the radius of the sphere. If we stand on this side of the sphere and look at different directions, we always have the feeling that we are top of a hill and the surface bends downwards. On the other hand, if we stand in the inner side of the sphere, we have the feeling that we are in a valley, and in an arbitrary direction the surface bends upwards. This is the property of positive curvature surfaces. There are also negative curvature surfaces, where in one direction we have the feeling that we are in a valley, but in the opposite direction we feel that we are on the top of the hill. Recall that for the curvature of curves we assign the sign depending on the direction of the curving. So if we have two curves bending in two different directions, then the Gaussian curvature computed as a product will be negative. So the saddle is a negative curvature surface. The trumpet is also a negative curvature surface. Usually the curvature on a surface changes from point to point. Let's take the example of the torus. The torus has a positive curvature outside and a negative curvature inside. Here I show a zoo of different object types, and the coloring describes the Gaussian curvature. We used rainbow colors. So green means zero curvature, red means positive curvature, and blue means negative curvature. The sphere has a constant positive curvature. An interesting object called tracticoid has constant negative curvature. We have seen that the cylinder as well as the plane have zero curvature. The torus has a positive curvature outside and negative curvature inside, and the curvature changes continuously. This is a Möbius strip, Klein bottle, or the so-called boy surface. Concerning these objects, the curvature changes from point to point. Euclidean geometry describes zero curvature spaces. So what if the curvature is not zero? For example, it's constant positive. Such a geometry or space is described by spherical geometry. Let us find the axioms of spherical geometry by checking first whether the axioms of Euclidean geometry remain valid or not. But first of all, we may say that this is a complete nonsense, because obviously on a sphere we cannot define a line, because if we move along a line, even if we started at the surface of the sphere, we will get farther away from the surface of the sphere, so we will leave our original space. This is a wrong argument. Recall that points and lines, these basic concepts are defined by the axioms implicitly. We cannot take the axiom of the Euclidean geometry and the concept of the line based on this Euclidean interpretation and enforce it onto the spherical space. The concept of line should be reinterpreted according to this new space. So what is line in general? Line in general is the shortest path between 2 points. So what is the shortest path between 2 points? Well, it's the main circle, which is defined by the 2 points and the center of the sphere. So these 3 points identify a plane which intersects the spherical surface, and the intersection is just a circle, which is called the main circle. The main circle has the same radius as the sphere itself. Airplanes usually follow these shortest paths, also called geodesics. Let's return to the axioms. The first axiom of Euclidean geometry says that 2 points define a line. Is it valid here? Well, usually yes, but not always. Because if we select, for example, the North Pole and the South Pole, then all longitude lines will go through these 2 points. Generally speaking, if we select 2 antipodal points on the sphere, then infinitely many lines can be defined. But if we exclude this special case, yes, it's true that 2 points unambiguously define a line. So we may say that the first Euclidean axiom is not valid in spherical geometry? No, because this is a wrong argument again. In fact, this is the same wrong argument when we tried to use the Euclidean interpretation of the line. In fact, the point should also be given a new interpretation. We may say that a point in spherical geometry is just a diameter of the sphere. Therefore, we can exclude those cases when 2 points are just the antipodal points. After these reinterpretations, I can replace first trial of our axioms, and then we can say that 2 points, using the interpretation of the point here, which means that the point is in fact a diameter, unambiguously define a line which is nothing but a main circle of the sphere, and also the geodesic defining the shortest path. So the first axiom remains valid. What about the second axiom? A line has at least 2 points. Yes, it's pretty obvious, it's still true. What about the third axiom, the parallel axiom? On the sphere, it is impossible to set 2 main circles in a way that they don't intersect each other. We may say that they always intersect each other in 2 points, but these 2 points are identical because they are antipodal points on the sphere. So the parallel axiom in spherical geometry is the following: 2 lines always intersect in a single point, which is nothing but a diameter. If we move an object on the spherical surface, then nothing changes. In other words, the space is uniform, similarly to the Euclidean space, so no matter where we are, objects look the same. And again, we can say that if we cut an object into smaller parts, then the sum of the smaller parts is the whole object itself. So summarizing, we modified only a single axiom, the parallel axiom. It may seem to be just a small change, however, it has important consequences. Namely, all theorems that are based on the original Euclidean parallel axiom will be invalid in spherical geometry. One of the examples is the angle sum of triangles, which is 180 degrees in Euclidean geometry, but it will not be 180 degrees in spherical geometry. It's easy to show. I give you an example. Let us find 2 points on the equator of the Earth, and the distance between these 2 points is 10,000 kilometers, so this is just 1/4 of the whole equator. And the third point of this triangle is just the North Pole. So this distance and this distance are also 10,000 kilometers. And when we turn from the equator towards the North Pole, the angle is 90 degrees. So here we have 90 degrees, here also 90 degrees, and as this is 1/4 of the whole equator, here we can observe 1/4 of the total angle, which is equal to 90 degrees again. All angles of the triangle are 90 degrees, so the angle sum is 270 degrees. The Pythagoras theorem will not be valid either. This is a super-right triangle because all angles are 90 degrees and all sides are equal, so obviously a square plus b square is equal to 2c square and is not equal to c square, as Pythagoras would say. This is a nice geometry and we can play with it with a big ball in our hands. But obviously it's a little bit more convenient if we have a map about the geometry. Then we don't have to deal with this big ball. A map is just a projection of the spherical surface onto the Euclidean plane. And as the sphere doesn't have a zero curvature, it has a constant positive curvature, this mapping must have a distortion. Maps always cheat. There are many different maps and they cheat differently. I just show you one particular example, the so-called Mercator map, which shows the angles in a correct way. However, Mercator map distorts distances and areas significantly. For example, on a Mercator map, Greenland has the same size as Africa, although in real life Africa is 14 times bigger. So how can we establish such a projection? Well, first of all, the sphere is enclosed in a cylinder and points on the surface of the sphere are projected onto the cylinder. This cylinder is stretched vertically in order to guarantee that angles are preserved, and Mercator developed this stretching formula. So if we have a cylindric map, then it's easy to unfold it into the Euclidean plane because the cylinder itself has also zero curvature. Let us see an application based on this concept. So here we see the Mercator map and here the sphere itself. And suppose we want to travel from Hungary to Canada, then Brazil, China, and finally let's return to Budapest. So this is the path that would be used by an airplane because these are the shortest paths. And on the sphere we can observe that indeed these are the main circles. Looking at these maps, it is not surprising anymore that when we travel to Toronto, for example, we can enjoy the view of Iceland and Greenland as well. And when we fly to China, the airplane stops in Minsk to refuel. Hyperbolic geometry is the geometry of constant negative curvature surfaces. The axioms of hyperbolic geometry is almost the same as the axioms of Euclidean geometry, with the only difference that we modify a single word in the parallel axiom. While in Euclidean geometry, when we have a line and a point outside of this line, there is exactly one other line that doesn't intersect our original line. In hyperbolic geometry, there are many such lines. Again, this small modification in the axioms has a huge impact on the geometry itself. This is a completely new world. In this geometry, the angle sum of triangles is always less than 180 degrees. The bigger the triangle is, this difference is larger. The theorem of Pythagoras looks like this. If we have a right triangle, a square plus b square is always smaller than c square. And all other theorems that are based on the Euclidean version of the parallel axiom must also be changed. Similarly to spherical geometry, hyperbolic geometry can also be examined on maps. Maps are projections of the hyperbolic plane, and they necessarily introduce some distortions. There are many maps. Here I just introduce you two of them, the Beltrami-Poincaré map and the Beltrami-Klein disk. Let us see them in action. Here we see the hyperbolic plane as a Poincaré disk, here as a Klein disk, and here we have a projection of the hyperbolic space itself. In these maps, the whole hyperbolic plane is projected onto the circle, so we can observe infinity here at the edge of the circle. Let us check whether the axioms of the hyperbolic geometry are true. 2 points define a line. Well, indeed, if I define 2 points, a line going through them can unambiguously selected. Note that these maps must involve distortions. In the Poincaré disk, this distortion means that lines will not look as lines in the map, but they are circular arcs arriving at the base circle orthogonally. However, here angles are preserved. In the Klein disk, lines look like lines. However, both distances and angles are strongly modified. The second axiom is that every line has at least 2 points. This is pretty obvious in both maps. So let us see the third axiom. If we have a line defined by 2 points and a third point that is outside of this line, then there are many lines that do not intersect the original line. So let's find another point, and you can see that all these lines pass through our third points without intersecting the original line. In fact, we have 2 special cases, and all lines in between these special cases belong to the category that they go through this third point without intersecting our original line. So yes, this is the hyperbolic interpretation of the parallel axiom. Let's see triangles. If the triangle is small, the triangle looks like an Euclidean triangle. However, if the triangle is big, we see that the angle sum is indeed smaller than 180 degrees. The angle sum is not relevant here because in the Klein disk, angles are strongly distorted. Angles are correct only in the Poincaré disk. And if I were able to draw an infinitely large triangle, the angle sum would be 0. Here we can check the angle sum. So in the case of our last triangle, the angle sum is only 6 degrees. The richness of hyperbolic geometry is often demonstrated with tiling the plane. Tiling means that we cover the plane with regular polygons. To allow a comparison, let us first examine the possible tilings of Euclidean geometry. So the question is, can we cover the Euclidean plane with perfect triangles? So let's take a perfect triangle and reflect it onto one edge. We have a second triangle, and keep doing this, we can establish a row. And if we reflect this row onto this edge, we can introduce a second row, and repeating this, the whole plane can be covered. So this is a valid tiling of Euclidean geometry. This tiling is called 6-3 tiling because we use triangles, and at a vertex of the tiling, exactly 6 triangles meet. Obviously, this must be the case because in case of a perfect triangle, the angle is 60 degrees, so we need 6 of them to produce the 360 degrees of the total angle. We can also tile the Euclidean plane with squares. This is a 4-4 covering because we use squares for sided polygons, and at a vertex 4 squares should meet, because in the case of a single square this angle is 90 degrees, so we need 4 angles of 90 degrees to provide the 660 degrees of the total angle. What about pentagons? So if we have a pentagon and reflect it onto one edge and reflect again on the other edge, the 3 pentagons will not produce a total angle. the internal angle of a pentagon is 108 degrees, and if we multiply it by 3, we still have 36 degrees deficit. Unfortunately, this 36 degrees deficit is too small to include a fourth pentagon. So pentagons are not good to cover the Euclidean plane. However, hexagons, six-sided polygons, are good. The internal angle of a hexagon is 120 degrees, so we need 3 of them to produce a nice tiling. Can we use polygons of a higher number of edges? Let us recognize that if we increase the number of edges, the internal angle also increases. And for hexagons, this internal angle is 120 degrees. On the other hand, to produce a valid tiling, in a vertex, at least 3 polygons must meet. Here 6 triangles meet, here 4 squares meet, here 3 hexagons meet. If we increase the number of sides further, the angles will be bigger, so if we multiply this angle by 3, which is just the minimum number of meeting polygons, we will have a result that is greater than 360 degrees, which cannot be, so there are no more tilings using higher number of edges. These 3 tilings are the only tilings in the Euclidean geometry, not in hyperbolic geometry. Because in hyperbolic geometry, increasing the size of a regular polygon, the internal angle can have an arbitrary value between the value of the corresponding Euclidean version or 0. By adjusting the size, we can provide infinitely many tilings, and even with a single version of the polygon, we have infinitely many variations. So for example, we can cover the space with triangles in a way that 8 triangles meet at a point, or when 9 triangles meet at a point, or when any number of triangles that are greater than 6 meet at a point. Similarly, we can use not only triangles, but rectangles, pentagons, and polygons with any number of sides. Here we used pentagons. In the first case, 4 pentagons meet. Here, 5 pentagons meet. Let's see this in action too. The same maps, the Poincaré map, the Klein map, and a projection of the hyperboloid. Let's start with triangles. Okay, this is not a valid triangulation because we can observe a gap. So in order to remove this gap, let us decrease the size of the triangle. So we have a nice tiling when in a vertex 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles meet. On the other hand, if we increase the size of the triangle, we can make enough space for an additional triangle when 11 triangles meet at a vertex. We can repeat the same operation with pentagons. Again, this is not a right tiling because there is a small gap, but I can remove this small gap. Here 5 pentagons meet in a vertex. Let's increase the size of the pentagon just to make enough room for an additional one. Here we are, 6 pentagons meet. And so on, we can use any polygon with any number of edges. Let's return to Euclidean 3D geometry for a moment, because valid tilings of the Euclidean plane have a close relative in the three-dimensional Euclidean space. These relatives are called Platonic solids. Platonic solids are polyhedra, where a single face is just a perfect polygon. The question is, how many such Platonic solids can exist? So let us construct these Platonic solids from valid tilings. We have to observe 2 things. First of all, in a Platonic solid, if we look at a vertex, at least 3 faces must meet in a vertex. On the other hand, if we add up the angles of the polygons meeting at a vertex, the angle sum must be less than 360 degrees. In a tiling, the angle sum was equal to 360 degrees, and therefore polygons didn't introduce any curvature, so they were in the two-dimensional plane. In order to make these polygons bound a three-dimensional volume, they must produce some curvature, so their angle must be smaller than that. If we want to use triangles to form Platonic solids, we should reduce the number of meeting triangles from 6. On the other hand, the number of triangles should be at least 3. So what are the numbers that are at least 3 but less than 6? Well, 5, 4 and 3. The corresponding solutions are icosahedron, octahedron and tetrahedron. The names are easy to remember if you speak Greek. Hedron means face in Greek, and the first part of the name is just a number in Greek, telling us how many faces a solid has. So for example, tetra is 4, octa is 8. So for triangles, we have only 3 options. What about squares? We have to remove at least one square in order to introduce the needed curvature to create three-dimensional bonded volumes. But the number of meeting squares must be at least 3, so the only option is that 3 faces meet in an object which has 6 faces, so this object is called hexahedron or the cube. If we want to try with pentagons, we don't have to remove any pentagon because we already have an angle deficit, which is an advantage right now. We have the option that 3 pentagons meet at a particular vertex, and the result is the dodecahedron. What about hexagons? To produce a valid 3D object, the number of meeting hexagons must be less than 3. Otherwise, we have seen that in a vertex at least 3 faces must meet. There is no number that meets these two contradicting criteria. There are no more options. The number of Platonic solids is just 5. I drew a B here because although it is not possible to create a Platonic solid with hexagons, this hexagon structure is very popular for Bs because this provides a very uniform isotropic decomposition of the plane. The Poincaré disk was also used in art by a famous painter called Escher. These are all tilings of the Poincaré disk, in fact the hyperbolic plane. Everybody can create his or her hyperbolic plane. These rectangles can be attached to each other in a way that more than 4 rectangles meet at a particular point. Of course, the resulting object will curve out from the Euclidean plane. It will curve out more and more, and sooner or later the surface will intersect itself. So we can conclude that in theory it is impossible to include the hyperbolic plane into the Euclidean space without intersections. Hyperbolic plane is not as strange as we might think. We can meet hyperbolic plane in our everyday life, and in fact the hyperbolic structure is in our own heads because our brain shows hyperbolic properties. A lattice, for example, demonstrates how the hyperbolic plane uses the higher dimensional space. We have one more geometry left, which is very important in computer graphics, and it is called projective geometry. Let us return first to Euclidean geometry and to its parallel axiom. Although we often say, as a non-mathematician, that parallel lines meet at infinity. But this is definitely not true in Euclidean geometry because, according to the parallel axiom, if we have a line and a point outside of this line, there is exactly one parallel line that does not intersect the original line. So in Euclidean geometry, parallel lines do not intersect. The main difference between projective geometry and Euclidean geometry that in projective geometry, infinity is also present. I mentioned the religious belief behind these axioms, and indeed, the question whether infinity exists or infinity doesn't exist is just a religious question because we will be never able to go to infinity, look around and check whether lines meet there or not. So this religious question is decided differently in Euclidean space and in projective space. As infinity is not a number, projective geometry is not metric, which means that unlike in Euclidean geometry, in projective geometry we do not have the notion of distances and angles. So it's a kind of more fundamental, simpler geometry than Euclidean geometry. Again, we may think that this is something strange used only by mathematicians, but this is definitely not true. We can experience projective geometry in every minute of our own lives because perspective just demonstrates projective geometry. So if we go out and see a rail track, we will have the feeling that these tracks will meet at the horizon. Or if we visit the Hero Square here in Budapest, follow the lines defined by these tiles, we will realize that parallel lines also meet at the horizon. As in computer graphics, we have to simulate the perception of the three-dimensional world, where perspective is something, a natural phenomenon. We have to study and exploit the properties of projective geometry. So the axioms are, again, very similar. There are two main differences. As far as the parallel axiom is concerned, in projective geometry, two different lines always intersect in a single point. In a way, it is exactly the same as the parallel axiom of spherical geometry. But on the other hand, there are no additional axioms providing the fundamentals of introducing metrics like distances or angles. So spherical geometry and projective geometry are very close relatives. The difference between them is that spherical geometry is finite and therefore it has a metric. Projective geometry is infinite and doesn't have a metric. In projective geometry we do not have parallel lines. All lines are similar. It is in fact a significant advantage from the point of view of a programmer, because parallel lines always introduce a problem in programming because parallel lines form a kind of singularity. When we are implementing a program that computes the intersection of two lines, we have to deal with the case of parallel lines as a special case, and in programming we don't like that. There is no such problem in projective geometry, because two lines always intersect. When we will describe projective geometry with numbers, we have to realize that Cartesian coordinates, which are very popular in Euclidean geometry, will not be useful anymore in projective geometry. And the reason is that there is no notion of distance, and Cartesian coordinates are based on the notion of distance. So we have to find a different algebraic framework for projective geometry. Let us visit projective geometry as an Euclidean tourist. You can imagine the tour as the following. Suppose we are standing on a planar form. I already prepared a few objects painted on the floor that might be interpreted as circles by an Euclidean tourist. I say that might be interpreted as a tourist because there are no circles in projective geometry, as there are no distances, and the definition of the circle involves the concept of distance. So they look like circles, but we cannot be sure that they are indeed circles. In projective geometry, we can do two basic things according to the axioms. If we select 2 points, we can define a line, and if we identify 2 lines, they meet at a point. So let's select these 2 points, and these 2 points define a line. Let's repeat it. Select this point, and this point introduces a second line. And as an Euclidean tourist, we would say that these 2 lines are parallel. Note that there is no such concept in projective geometry as parallelism. Let's repeat the same operation. I select again this point and that point. We will have a third line and a fourth line here. Again, we might say that these are parallel if we look at the scene from an Euclidean glass. let's introduce a third pair of lines, this one and maybe this one. So these pairs of lines may seem to be parallel to an Euclidean tourist. Okay, now let us lift our point of view and let us turn right and forward a little bit. And we arrive at this particular scenario. What we see here is that our original parallel lines intersect here, here and there. These are normal intersections, and intersection define a point. So we have a point here and we have a point here. Okay. These points are at infinity because they are defined by two parallel looking lines, and connecting two points at infinity we see that the line defined by these points also go to the intersection of the third pair of lines. So we may say that this purple line represents infinity, and all infinities are on this purple line. So this is our universe, this is infinity. Interestingly, we see something beyond infinity as well. So what is this? What is beyond infinity? To understand that, let us turn to the left slowly, keeping this infinity in our sight, and let us remember that we were examining a blue point and we were asking what is beyond this purple line at this particular blue point. Let's go back. Infinity is always there. And we arrived here. We should realize that we see the same blue point and light green point we have already seen when we were turning to the right. This is infinity, and we have something on the other side of infinity. So we have the same scene beyond infinity on the right and beyond the infinity on the left. In fact, when we were standing close to infinity and looking to the right, observing these points, we were standing here. We were asking the question, what is beyond infinity? So what is beyond infinity? Beyond infinity is our space again. So this is a circular structure. If we go beyond infinity, we are back in the space from where we started. So we arrived at the end of this introductory chapter on geometries. We have got acquainted with various geometries that differ only because of the small modification of the axioms, especially the axiom of parallelism. In Euclidean geometry, as far as this parallel axiom is concerned, there is exactly one line that goes through a point and doesn't intersect the original line. In spherical geometry, there are no such lines. Spherical geometry describes the positive curvature of surfaces. In hyperbolic geometry, there is more than one such non-intersecting line, and in projective geometry, similarly to spherical geometry, there are no non-intersecting lines. And the difference between spherical and projective geometry is that spherical geometry is metric, projective geometry is not metric but includes infinity. These geometries have their special feeling. In Euclidean geometry, visibility rays emanated from the eye diverge. That's why objects which are farther away look smaller. This is a normal perspective. In hyperbolic geometry, these rays are hyperbolas, so they diverge even faster. As a result, objects that are far away look even smaller than in Euclidean geometry. The most interesting feeling is given by spherical geometry, because here visibility rays initially diverge, but after that they will converge again and meet at the antipodal point of the eye. So objects that are very far away look as big as they were right in front of our eye. I close this talk with 2 videos where you can enjoy these feelings. Thanks for your attention.
Millió hatvány létezik, még kiszámítható, de a pontkör hatványa is ugyanolyan jó. Nem lehet ám minden problémát lerajzolni, néha hát meg kell gondolni.
Nem csak a geometria a menő, néha az algebra is jó, mert abban van az erő, lehet oszthatóság vagy prim tényező. Nem csak a geometria a menő.
You